Now, first of all, I should say cheated a little bit. So I distributed texts of what I will not be talking about. No, it's close to what I just decided. It's too formal. There's a problem with writing text. It becomes very formal. So.
I shouldn't place it.
But they said that it's joint work with Arkady Bernstein and Sasha Braverman, and names are here. So, in a sense, it's very much related to, for me, first of all, to ideas which I learned from Gelfand in my youth of how to think about representation theory, and to works of Pitetsky Shapiro, who's also insistent on working with gamma functions. Now, the main idea is to try to explain, and maybe in some way to show, why the theory of representation of groups can be a part of algebraic geometry. What it means is the following. If we have a group and want to study representation of a group, it's good not to know over which field. So when I say group GLN, of course GLN is just a sequence of words, not a group. I have to tell you field or ring, and then I take GLN over some field F, and I can take representation. But I would be, on the other hand, algebraic geometry teaches us that considering points is the last thing you do. You continue as much as you can without any knowledge what is your field. You work with variety, and the last moment you go and look to points. So what I try to explain in what sense and how I could think about the theory of representations of groups or over fields without knowing fields. It's not the first work in this direction, and say character sheaves of Lustig is a very important example of a finite field of some objects, which are algebraic geometric objects, and trace of Frobenius, the function obtained by trace Frobenius, gives you essentially characters of representation. The objects are algebraic geometric. I want to try to do it so it's over periodic in a local periodic half-time global field on an example on some problem, which is the problem of lifting. But I'll start with something absolutely elementary and stupid. It's just I want to explain, since not everybody here is algebraic geometry, that difference between variety and points of a variety. Algebraic variety. I give two examples which I'll need.
Variety without points.
So variety is very different in notations. If I underline a letter, it's variety. If I don't underline the letter, it's points of variety. So suppose F is a field. Right now is arbitrary field. So X an algebraic variety. Then X is X of F. As a points of variety, and essentially I will try to follow these notations. Now, I give you two examples when it's important to distinguish between varieties and algebraic varieties. So in general, it will be following. If you have an algebraic variety F, and you have X, and you have a map into another algebraic variety, then of course this thing induces the map on the level of points. But if the trivial thing is the following, F surjective does not imply that F is surjective. And the same in sense to do for injectivity. Let me give you two examples of the map which I'll need. And in some sense, a lot of representation theory goes around these two examples. So I'll go to examples. So let G be a reductive group. a split reductive group. So G equal GLN is a good example. I could restrict myself, but some phenomenon that doesn't appear, but for people who are not familiar to anything else, it's perfectly fine. So we have G contains a Borel subgroup, which product of T times U. For GLN, it's diagonal matrices and upper unipotent matrices. So we have a Weil group, W, which is a normalizer of T, mod T. It's a algebraic group, but it's sort of a trivial action Galois group, which has a group of a point. W acts on T, and we have two important maps. We have first important map, alpha, which is map T into T mod W. This is a very important map. And we have another important map, which I'm going to discuss, is a map of, let's call it this, and the map beta, which is a map from G in T mod W. This map is, for GLN is taking characteristic polynomial. To any matrix, you can associate characteristic polynomial, or another way, take any matrix, so it's a regular matrix. You can bring a diagonal form of algebraic closure, but not uniquely up to symmetry. So the map in the Gaussian space is well defined. Now, let's talk about properties of this map. One is, so example, just if G is GLN, T is elements T1, Tn, then alpha.
Beta is what, diagonalization?
What?
What is this map from G to?
This map, take invariant polynomials. The claim is that ring of invariant polynomials on the group is isomorphic to ring of W invariant polynomials on T.
Despite the fact that not all matrices are diagonal.
It's true, but ring of polynomials is the same. So the map is well defined. Just mapped with a spectrum of invariant polynomials. Now, from now on, I assume that all elements are always regular. I ignore such small detail with existence, non-regular. It will not be important here. It will be important somewhere else, but not here. So, just if you can see lambda T1, Tn is a product for I equal 1 to n, so some, I don't know, tau minus Ti. So this is a map from roots to polynomial, characteristic polynomial. And beta is also taking characteristic polynomial. So now two remarks. First of all, alpha bar is surjective. But alpha is not. Of course, not any polynomial has roots defined on the field. This is existence of all representation different from principal series representation life is based on this observation. The second thing is, let's consider beta. Beta, of course, defines a map from G. It's surjective as algebraic variety, just map into quotient by definition. Points, because I can give you a polynomial with what? Yes, because if I give you a polynomial with coefficient over field, not necessarily roots are over field. No, field is not closed. Our closed, algebraically closed field, it's the same, but our fields are not algebraically closed. The second thing is you have a map G. Of course, you have map in T W of F. I write like this. I can write it. It's quotient of variety over F. It's naturally composed into G mod adjoint action of G. It's clear, remember? And then you have this map. Now, let's call this map beta tilde. Here, it's important thing is beta tilde is an embedding.
Impossible to change or leave the
Is it possible to see now? Yes. Okay. So then the following thing. I want to leave this blackboard, so.
Again, when you divide by adjoint, G is not quite right.
No, it's a set of points. G is a set of points. When I this is a set of points, it's a set of conjugacy classes, and of course we can have map here. It means map on the level point in G invariant. And now, there is important thing. If G is GLN, then beta tilde. Okay. All right. Try it here. If G is equal to GLN, could you see now? Then beta tilde. No. Okay. That's beta tilde is an embedding. As I say, ignore existence of unipotent matrices. It means if two matrices, two regular matrices, have the same characteristic polynomials, then they're conjugate over field. Now, in general, beta tilde is not an embedding. So let me give you an example. If you consider, if, so say that's all right, if f equal to r, g is equal to SL2, then, so g prime is equal to 0, 1, minus 1, and g double prime is equal to z minus 1, 1, 0. Then beta tilde, beta of g prime is equal to beta double prime. The only characteristic polynomial for SL2 is trace. And it's easy to see the trace of these two matrices are conjugate, but add g of g prime not equal add g of g double prime. In other case, these two matrices are conjugated over algebraic closure. Therefore, invariant polynomials don't distinguish them. But they're not conjugated over field. So this phenomena, on the level, on the language of representation theory, creates L packets. So L packets are responsible for this kind of non-algebraicity. Is responsible for L packets. Okay. Now I want, so this was not too short of introduction. Now I want to describe representations. We start with representation of a torus. So I start with algebraic group. Simplest possible algebraic group is a torus. So the simplest torus is, so GM is, by definition, the multiplicative group. So GM of F is F star. So it's algebraic group such that the corresponding. Now a torus T is an algebraic group isomorphic to GM in some power n. Just product to a torus, but not canonically isomorphic to a torus. Now, there are a couple of what? It's split. Everything is split. I said at the beginning it's a split reductive group, and all groups are split. Nothing. I want an orange. So, for a torus, we can describe couple. Torus is easy to describe in terms of lattices. So we do the following: we have couple of groups. We define X star of T is a group which set of homomorphism of GM into T And then you can write canonically if you want. This is a lattice. This just a finally generated abelian group. And if you can write T is equal X star of T. Then in some sense with GM. You have another important group you can define, a group of 12 characters, which by definition home of T to GM. There's a group of algebraic characters. And you have a natural pairing, X star of perfect pairing, X star of T into Z. So this is a basic structure which we have. Now let's study representation of this group. So assume that F is a non-Archimedean local field. So you can assume, if you want, that it's field of periodic numbers and nothing will be lost under this. Let's study representation of the group. So T is a okay. Let O in F be the ring of integers. So in this case, O is just ZP. Now let T be a torus, always split torus, over F. Then K is by definition T of O is a maximal compact subgroup in T. This is a group of integer matters. Let T hat be the set of irreducible representations, complex representations of T, T unramified, the subset of representations trivial on K. Now let's describe what I said. Unramified is by definition a representation of T or character T is unramified if and only if it is trivial on K. This is definition. So let's describe this set T unramified. By the definition, now since the group is commutative representation, it is the same as character. T unramified is home of T mod K into C star. Now you can easily see that it is the same using interpretation of T. It's the same as home X star of T into C star. Just natural isomorphism. T mod K is the same as T, which is equal to X star T tensor C star. And we define this to be the dual torus of T. If you want, I can. So dual torus of T, we start with torus T. The dual torus is a complex torus, which defined in this way.
So LT means nothing.
It's the definition. The definition of LT. There's nothing else. Definition of LT.
But LT alone means nothing. Only LT of C.
Oh,
It's not an algebraic group.
it's algebraic group over C, but over C group are easily identified with points.
Yes, somehow C star.
What?
Power
It's about, yeah, it's a torus. It's just torus.
X star of T confused me. It was
It's a lattice. This is just a lattice. It's just number of torus. Just okay. So let's see what we have. Lemma is that T unramified is in 1-1 correspondence, just equal to complex points. I'll just write this group. Now let's go to arbitrary. So this we understood very well. Torus, unramified representation of torus. Now let's deal with arbitrary. Let G be as before, arbitrary group. So as before, G contains B, which is a T mod U, the same decomposition of algebraic closure. So G hat is the set of, I should say here K is G over O, it's just integral matrices. The set of irreducible representations of G. No. G hat unramified is the set of all pi G in the outer morphism of some space V, such that there exists V element V minus 0, KV is equal to D. If there exists K invariant vector. This is the definition of the. It's always one dimensional if it exists, and no. There are no finite dimensional. Complex representation, this is what we want to study. Theory representation studies this set. A set of reducible representation of group, of p-adic points of our group. Complex representation of p-adic group. What? Yeah, unramified G, K invariant.
They're infinite dimensional, finite dimensional?
They're all infinite dimensional except one dimensional. No, of course not. Of course not. Okay, let's not. Smooth representation if you want, but let's not go on. There's only one way to define it, and you know it.
Well, I know.
It means you assume that the representation is such that stabilizer of any vector is open. Stabilizer of any vector is open. We consider such a representative group as stabilizer is open. Okay. Now we have a natural map. We have a map, very important map, let's call it R, of T irreducible, T unramified, into G unramified. The any character chi. What? So any character chi goes in representation pi chi, which is just induced representation from G to B with the character chi, when you understand unitary induction. Now, claim lemma 2, which is very easy. A, R is onto, and B, moreover, R, there is only unique sub-representation with K invariant vector. So you're right, but once more I ignore this. R is W equivalent. And C, R induces an isomorphism, which are also known I, on T unramified mod W isomorphism in G unramified. Now there is the following step. There exists canonically, so it's a complex group So the canonical one, canonically. Define. I will not go into definition. GL of C such that with, let's say more precisely, with maximal torus isomorphic to TL of C. This is called dual group. Canonical isomorphism. Construction gives you canonical isomorphism. So example which is important. I just write two examples. A, G is equal to GLN. GL is GLN of C. And B, G is equal to SLN. GL is equal to PGLN. There are other ways. Now let's combine everything. Lemma 1 plus lemma 2 imply G unramified is the same as conjugacy classes of GLC. Once more, I ignore the existence of unipotent classes. As always, don't go into the discussion. But this is exactly immediate. So we have now such parameterization of unipotent classes. Now let's go to the global situation. So this is what? Okay, we ignore reals because it's only 1 point. We'll go to global situation. Everything works over real, but I just simply don't want to go into discussion. Since I can avoid it, avoid it more. Now, I will not, so to say, change notations, but now I assume, and I think I'll try to keep on this line, let F be a global field. So if you want, you can assume F equal to Q will be no difference in understanding. P, the set of places of F. So for Q, it's all periodics and real. A, the ring of adapts. G, split reductive group over F. Then GA, which is by definition G of A, is a locally compact group. Well, what are you, Dennis? What's your question?
I was trying to remember whether Adele's included the reals or...
Yes, they do. They definitely do. They do include. You see from the next statement, G in J, a discrete subgroup. This, you see, it has to include real. Now, any irreducible, what? It depends if it's semi-simple, it's fine volume. If it's reductive, it's not. So I will ignore these differences. Any irreducible representation pi of GA has a form pi is a tensor product of pi over local fields, where pi p is, of course, irreducible representation of our group GP, and pi p is in unramified part for almost all p. This is your general structure. Reducible representation. Now, we say that pi is automorphic if it is a sub-representation, let's say. The quotation marks are to prevent questions of people who know. A sub-representation of the natural representation of GA on L2 of GA mod G. So this definition of, now we have remarkable result for GLN, which very much related to the property of GLN we discussed before. And here, if you want, we can define the lifting. So there is a following theorem, multiplicity one theorem. Let pi prime, pi double prime be automorphic representations of GLNA.
Gammas are not specified. Yeah.
What?
There's some stupid gammas inside. Yeah, you mean something.
Which is gamma? G is G of F. G is G of F. It is gamma.
Okay. Well, no, you said. Well, you said.
G is G of F, always. So, automorphic representation is such that pi prime p is equivalent to pi double prime p for almost all p, then pi prime is equal to pi double prime. Okay, this is a theorem. Now I can formulate the problem of lifting.
What? P prime
Then, sorry. Then they are equal in all points. If you have two automorphic representations, which are local components coincide in almost all points, then they coincide in all points. The representation theoretical analog of Chebotarev's theorem.
Coincide for almost all points.
For almost all points, then it coincide everywhere.
Almost found it really.
Yeah, almost fine.
Can you evolve it at small density?
Yes, zero density is fine, but I will not go into it. It's easy to prove, but I will not go. Now, let me now define lifting. So let G be as before. Rho is a representation, algebraic representation, finite dimensional representation in G, L, and C. And this group is equal, as we said, GLN, dual to GLN is GLN itself. Now, let pi equal tensor product of pi p be, I have to say something before I go. So, we have for any place P, we have a map. That's this I should do before, but we'll do it here, which is the following. T hat of P unramified, which is equal, as we know, conjugacy classes. How I formulate it? Yeah, conjugacy classes of GLC. This is written there. Now I apply rho that maps it to conjugacy classes of GLNC. If I have representation, then of course any conjugacy class I can, the conjugacy class, which is GLN FP unramified. So we have very important map, which I could define rho unramified. Pop, not here. Rho unramified, which maps unramified representation of GP into unramified representation. Now I can formulate lifting conjecture.
You can repeat the last line. You have a map from
Unramified representation of G in any local place to unramified representation of GLN. It's just composition of this isomorphism.
the same place.
Well, same place, for any place. Now we can take lifting conjecture. The lifting conjecture.
This n is going to be compared to the word example. Jesus.
There's no n in example, but if it's just n is the index.
So any n that is anyway.
G is not related to n. You have to take any representation of this group. G is not GLN, so that is, doesn't have any intrinsic meaning. The lifting conjecture. It consists of two steps. A, for any automorphic representation pi equal tensor product of pi p element p of G, there exists an automorphic representation. Let's call it sigma tensor product, P, sigma p of GLN of GLN. Oh, sorry, automorphic representation of J, automorphic representation of L group, such that sigma p is equal to rho hat of pi p for almost all p. This makes sense because this representation is unramified almost everywhere. So this is uniquely. Now, multiplicity 1 theorem tells that this representation sigma is well defined, because uniquely defined. And B is, the conjecture B is the map pi p into sigma p does not depend, is defined locally. It means if we take two representation pi, which the same component in point P, then the corresponding representative sigma will have the same component in the point P. In other words, no. A was for one representation. We take one representation P, we construct the automorphic representation. Now we take another representation P prime, unrelated to pi in any way, but which happens to coincide in a point P. Then we define representation sigma prime, which exists for conjunction. I mean, to its component of P place. The claim is that we'll get fine.
So the second was not automorphic. Now B concerns not automorphic representation.
No, B concerns local statements, that it depends only on local thing. It tells the following, that if we take two automorphic representations, pi and pi prime, such that local components in the one point P are the same, that for corresponding representation, sigma and sigma prime, their local component in the same P are also the same.
Even if the place is ramified.
So, in other words, it means there exists a natural map rho hat of G FP into GLN FP. It means there exists some local construction, I didn't define it at all, local construction of which is associated to any reducible representation of a group in a local point, some representation.
You use also the geometric construction.
Algebra geometric will come in a second. There exists a construction defined on the level of representation. Now, I want to propose a formula for this construction. And
It's like you're saying you can reduce the original row mod P.
it's not reduce, it restrict.
Treat it.
Okay, so let's try to do it. So we do it in the following 3 steps. So first of all, we consider a case when G is equal to T. In this case, we can construct lifting oh no, I'm running too fast, unfortunately. Cannot do it. All right, so I'll stop somewhere before I start. That's fine. So, how to describe rho? So idea would be to any reducible representation of G associate representation of GLM. But what does it mean to associate a representation? Representation consists of vector space and an action in this vector space. But vector space, we don't know how to present vector spaces. The only good way we know how to present vector spaces as functions somewhere or sections of some line bundle. So some set is associated with construction. But this set is not canonical. So if we want to produce an explicit construction, then we have to produce more than what we want. It's not clear why should we succeed. So I want to describe this map without even mentioning the space of representation. So let me explain how to do it. One, we define a function gamma or G, L, and F. So let F be a local field. I don't think I have time to come back and to discuss global stuff anymore, so we restrict to local field. Now we discuss B, which is a local construction, and then we try to have time to go. So B from GLN, F head into complex numbers. We define a function. 2. If we know rho head of G into GLN F head, we can construct the function gamma rho of G, which is just composition of gamma composed with rho head on G head. One can show the knowledge of this function completely determines representation. I'll talk only about this function. 3. How to describe function on representations. One can show, if you use some assumptions on rho, which I assume there exists, that there exists a function phi rho G, things are called phi rho G bar, on the group G, such that gamma rho G is the Fourier transform of F bar rho G. By Fourier transform means that is for any pi G into automorphism of V, we have as a class function, exists a class function. For finite groups, we know it very well. We have integral over G, F bar rho G of G, pi of G dg is equal to gamma rho G of pi identity. Now just usual Fourier transform in a finite group, which gives you a 1-1 correspondence between functions on the space of representations and class functions. So this is a function which we want to construct. Now, what? The function depends on G. It's class function on G. Now, there are the following claims, and well, whether I have time to say anything more is not clear. Okay. Now, the program of defining function goes into 3 steps. How? Yeah. Let's do it one more, I think. Now, since row head collapses L packets, let's call prime here, we assume that, yeah, I unfortunately erased what I wanted, but okay. What? Well, it means if you have 2 representations which are very similar for G, there on G, I would have representation which is very similar and undistinguishable. Image in GLN should be the same. Multiplicity 1 essentially says it. We assume that f rho G, the function, can be written is beta star of f rho G, where, so beta is before map from G into T mod W over F, the same map as we had before, where f rho G is a function on T mod W. In other words, we assume the function has the same value on the elements. Now, so we want to write a function here. So how do we write a function here? So how to write f rho G? So the idea is the following. A, we consider the case when G is equal to torus. Then we can write explicitly a function, W function, f rho T on T of F. This function is W invariant. Now, the second statement is, and this what I need 5 minutes to. Yeah, we'll discuss it in a second, the shape of a function, very much related to Spencer's law. But now, conjectural claim, say conjecture, there's no claim in general. F rho G is the descent of, sorry, the bars here important, on descent of F rho T. Now, what does it mean to descend a function? Of course, you can just compute value of the function on elements which are image of that, but the map alpha is not onto. So how to descend a function? So let me talk for 5 minutes of what is. So you cannot, of course, descend the function, but you can descend an object which is called algebra geometric function. So let me define a notion of algebra geometric function. And this is really what I wanted to talk about, but we can start. So, algebra geometric function is defined over any variety, over any field. So let y be a variety. An algebra geometric function on y, algebra geometric function over y is a quadruple x p f omega, where p x y is a smooth map.
X is the variety.
X is a variety, it's a smooth variety. Of the same field. Smooth variety, yeah, smooth variety, it's a smooth web. Yeah, what I need is map smooth, but in our case, it's y is smooth, so everything is smooth. F is a map of x to a line. Omega, this is p. I'm sorry if they look the same, but I didn't write them twice. This is top relative form, omega, top of x over y. Volume, top form. Now, if this is notion of algebra geometric function, it's top volume form. If f is a local field, let's define this function, we'll call it phi. Phi is a function. If f is a local field, we denote by f bar the function on y, it's a set of f points, sorry, it's algebra geometry here, given by is it possible to see here, or I can write here. The following, f bar of a point y is equal to integral over p inverse of y. It means f points of p inverse of y. Psi of f, so let's call it x element here. Psi of f of x. Norm of omega. Top form on a fiber divides a measure on a space of periodic point. Your psi is one for all non-trivial characters. So this data we find called algebra geometric presentation of a function. Now, suppose let W be a finite group acting on Y. A lifting, an action of W on phi is the action, an action on X compatible with P F omega. Now, if we have an action of W on F, we can descend F to omega on W. We just take quotient, so let's call it F mod W on W. F mod W is just X mod W P F omega. Now the conjecture. Now, now that statement and conjecture, and then.
This situation is quite different map there, yeah?
No, that's exactly. So now the claim is, the problem is to finding this. Yeah. Claim. The function for any t and rho, as before, rho, so it's a tier in GLN, the function f bar rho t on t has a canonical algebra geometric presentation. B, in a number of cases, we can construct an presentation, canonical presentation, we call it phi rho t. We can construct an action of W on phi rho t. Let phi rho g be phi rho t mod W on, so it's on t mod W. So in a number of cases, we didn't check, but in a number of cases, we can show that phi bar rho g defines a lifting. So once more, the definition of a lifting, of a lifting, was reinterpreted as a construction of some very special function on the set. The claim is that, at least in a number of examples, these functions obtained by descent from the corresponding function on the split torus.
There are two different tori in G and GLN, yeah?
So it would be in G. Torus and in G. GLN torus will not appear. So I didn't tell you. So you ask me, where is GLN? This is the general construction. T was always torus in G. Rho.
There was representation.
It's a representation of a torus. Now, so what you do? You take, okay, sorry, so let me know. So you start with representation rho L of GL into GLN, yeah? And then you just restrict it, rho L restrict to T. This is what you start. If you have any representation of a dual group.
Yeah, out of this makes algebra geometric function.
Yes. From this you make an algebra geometric function, and then you construct. Now, the action of W, construction of W in examples when we construct, is very much related to geometrization of crystal bases. But it's a separate story. But Kashevara has a notion of crystal bases. So by saying that it's always, in something, the structures appeal in finite dimensional representation, they are very much related to the structure of static representation. It's just, it's a separate discussion how related, what related. But the lifting is not easily written. You need some machinery to write it. It's not naive. Naive liftings do not work. So I can either give an example. I think I stop if people ask questions, and maybe since it's time for discussions, I think it's time for me to stop. And
So we can either have a discussion now or just postpone until the evening. Maybe Gilles needs it.
Maybe some questions, we can still remember.
yeah, I think it's better if people ask questions now. I prefer to answer now. Yes.
Can you say in just a minute what is the x and
Yeah, of course, I can tell you immediately. The construction is very explicit. So let me give you a construction. Construction is absolutely explicit. So suppose we have rho is a map of dual torus into GLN. Then we can write what? Then we can write, of course, since it's a torus region, that rho is direct sum.
Maybe white algebra gets it down.
No, we see visualize there. It's possible.
Okay, yeah, I can write on any. Is there any blackboard which is good for everyone?
Okay. No, this one.
This one. This one. Okay.
No, it's okay.
The only thing is I don't want to just. So if it's fine, it's fine. Let's put more. So we can write rho as direct sum of characters. Since it's representation of a torus and GLN, we can write the word character chi I is a representation of TL, mapping TL into C star. So chi I, in other words, is the element of X hat of TL. Not just character of TL. But this is the same. The relation with torus and dual torus was exactly the characters of one are co-characters of another. Now, consider, let X, which we want to produce. So Y, of course, now. So in our case, Y is T. We want to produce an algebraic geometric function on T. So Y is T. So take X to be product of GM from I equal 1 to N. No, if you want it, just GM in the power N. Now we have to define maps. The map P of T1, let's go, lambda 1, lambda N, is by definition chi I of lambda I product over I equal 1 to N chi lambda. So chi I was a character of T, is a co-character of torus. So this is once more is home of GM to T. So I can evaluate it for any point lambda. This is a map. The function f of lambda 1, lambda n is sum from I equal 1 to n, lambda I. And the form omega is dx over dt. You have, each one has Haar measure, each one has invariant form. And so ratio defines invariant form of the fibers. So this is the form. Now I can, there is simplest case, one case when if you want I can write the action of W, you'll see.
So this W is tricky.
W is tricky. I can present one case when you can see. So let me do it. So take first non-trivial case. What? If you have a question, there's no questions like this. So let me, I can describe it, but let me first, I can answer this question as next question, but let me first answer this. So in this case, we have the following, so we take group G is, following is GL2 cross GL2 mod lambda identity, lambda inverse identity. Then GL, no, this is not, no, sorry. G I take matrices A, B, element GL2, such a determinant of A is equal to determinant of B. Then the group GL is GL2C cross GL2C mod lambda identity, lambda inverse identity. Now we take a representation rho of, let's take A of alpha beta is alpha tensor beta. This is well defined on this, which is a map of G into GL form. Now let's see what are the tori in this case. In this case, T is a set of all matrices, alpha 1, alpha 2, beta 1, beta 2, such that alpha 1, alpha 2 is equal beta 1, beta 2. X is a set of matrices like this. P is the map A, B, C, D goes to A, B, C, D, A, C, C, B, D. So W is, of course, zemo 2 cross zemo 2. Now, in the omega is what you want. Now, you can think in this way that a very natural action of this group here. The action, you can just interchange rows and interchange columns. The thing is, this action does not preserve the form. It changes the sign. Now, and of course, f of A, B, C, D is A plus B plus C. Now, if you see, now you know already how your action should be compatible with P and F. So essentially, but now if you consider a map from X to T cross A1, which is, so to say, P cross F, you can easily see that this is double covering. And now, there is one action of W which preserves covering, but it's the wrong one. So there is only one choice here of an action of W which preserves everything. And this action is given by the formulas. It doesn't matter, I write one of them, but for example, tau star of A under one of action is C, B plus C over A plus D, and so on. It's birational action. So this action of W, as you can see in this case, it's not a naive action. But in this case, you can do it by hands because it's unique action preserving. Okay, now I think I'll stop. Yes?
Okay, I think we should stop.
Yeah.